Okay, we're going to finish up by going through four review problems. And the first one goes back to friction. Number four, we have a mass of 120 kilograms. And the first question is fairly straightforward. It says, what is the friction force, the static friction force, for this mass being pushed along a wood table or a wood surface? And that friction force is the coefficient of static friction times the normal. And in a flat situation, the normal is going to be um, its weight. So we have the coefficient of static friction wood on wood, which is 0.5, times the mass, which is 120 times 9.8. And if we do the calculation here, we get 588 newtons. Now then it says, what is the acceleration if after it starts moving the friction or the force that's continued to apply is equal to this initial force. So if you continue to apply 588 newtons after it begins to move, what's the acceleration? Well, F net is going to equal to this force minus the kinetic friction. And so that is going to equal the mass of the object times its acceleration. So its acceleration is going to equal to F minus the kinetic friction force divided by the mass, which is going to be 588 minus the quantity of 120 times 9.8 times the coefficient of kinetic friction, which in this case is 0.3, divided by the mass, which is 120. And if you do the math here, you get 1.96 meters per second. So pretty straightforward problem. Number 25, you start out with a radius of 2 millimeters. The density is 1.00 times 10 to the third kilograms per meter cubed. And we know that the mass is going to be 4/3 pi r cubed times the density. This is the mass. If we multiply that by 9.8 for the gravity, we end up with the weight. And the weight is going to equal to 3.35 times 10 to the minus 2 newtons. And so we can use that. So the first question actually is, if there's no drag, what is the final velocity? Well, the final velocity is going to equal the initial velocity. The final velocity squared is going to equal the initial velocity plus 2 times gravity times the distance that it falls. And we're assuming that this is not heaved, so the initial velocity is 0. So that means that the final velocity is going to equal the square root of 2 times gravity times the distance that it falls, which is 5,000 meters. If we do the math here, we get 313 meters per second. Now, if there's drag, we know that FD is equal to 1/2 C rho cross-sectional area V squared. We know that C is equal to 0.45. We know that rho is equal to 1.00 times 10 to the third. And so we can rearrange this so that V is equal to the square root of 2 times FD over C rho A. And FD is equal to this weight that we calculated over here, so it's going to equal 2 times 3.35 times 10 to the minus 2 divided by 0.45 times 1 times 10 to the third times the cross-sectional area, which can be also gotten from the radius. If you do pi r squared for the area from the radius, you get 1.06 1.26 times 10 to the minus 5 meters squared for the radius. And so we put that in, 1.26 times 10 to the minus 5. All of this is, we're going to take the square root of, and we end up with 9.7 meters per second. So we see that the difference here is this huge drag force that's operating on the situation. Number 34 is a review question from the Young's modulus. We have an original length of 20 meters. We have a diameter of 4 centimeters, so a radius of 2 centimeters, or 0.02 meters. We use that to calculate a cross-sectional area. The cross-sectional area calculates out to 1.26 times 10 to the minus 3. And we have a force of 900 newtons. And so if we put this in, the shear is delta x is equal to 1 over the shear modulus times force over cross-sectional area times the original length is equal to 1 over the shear modulus, which is 25 times 10 to the 9th, times 900 over 1.26 times 10 to the minus 3, times the original length of 20. So delta x, or the change in lateral motion, is going to be 5.7 times 10 to the minus 4 meters, or 0.57 millimeters. The last review is similar. The only difference, now we're working on number 39. And number 39 is a force going straight down onto an object that's at an angle of 30 degrees or 20 degrees, excuse me. So this actually gets divided up into an x and y component by this angle. And so the compressive force that is straight down, the length of the object, another way to look at this is to draw the pencil straight up and down, and the force at an angle of 20 degrees. And so you have a shear force and a compressive force. Okay, so the compressive force we'll call Fc, which is down is this way, which would be the long way, would be 6 times the cosine of the angle, and the shear force is going to be 6 times the sine of the angle. Starting with Young's modulus, delta L, so the compression is 1 over y, force over cross-sectional area times the original length. We know that for hardwood, the Young's modulus is going to be 15 times 10 to the 9th. The force is 6 cosine 20 degrees. The cross-sectional area is calculated from the radius, which is 3 times 10 to the minus 3 meters. So you take pi r squared of that, pi times 3 times 10 to the minus 3 squared, and then the original length is 2 centimeters or 0.02 meters. And if you do this calculation, you end up with a compression of 2.66 times 10 to the minus 7 meters, which is pretty small. And delta x is going to equal 1 over s, the shear force over the area, times L0. So you're going to change this to the shear modulus, which is 10 times 10 to the 9th. This is going to be s, or 6 times the sine of 20 degrees over the same area calculation and the same length. And in this case, the delta x is going to be 9.67 times 10 to the minus 8